Yeah. The next thing is we are going to start now. Perfectly inelastic collision. So when we are discussing perfectly elastic collisions, two conditions we discussed, right? What are the two sufficient and necessary conditions that are required for anyone to say that the collision happening is elastic? The same thing we are going to do here. What are the necessary conditions so that we can say that the collision is perfectly inelastic? Okay. So the first and foremost would be after collision, bodies stick with each other. Okay. Here if we are going to do the questions in which a car is approaching on a highway and there is a fly also, then here this condition would be satisfied. That is what we see in the general life, right? If a fly like approaches the window of your car on a highway when your car is at like a very high speed, then instead of like striking and going away from the car, it sticks to the window, right?
Mm-hmm.
So if that question comes in this topic perfectly in elastic collision, then you will like see that thing happening. Okay. Now again, because this is a collision, because there is no external force, only there are internal forces. So momentum is again going to be conserved. Okay.
Mm-hmm.
Not momentum is conserved, but rather momentum remains conserved. Remains means throughout the motion it is conserved. Okay.
Yeah.
And kinetic energy initial is equal to kinetic energy final on the system if we are applying. Okay, here I have not written that kinetic energy remains conserved. I have just written that kinetic energy initial is equal to kinetic energy final. Okay, why so? Let's see. Suppose there is a mass m here, m1, it is moving here with u1. And here there is m2, it is moving with u2. Obviously u1 is greater than u2 because collision is required to happen. Okay, now after the collision, when they have stick to each other, something like this, m1, m2, and they are moving with some common velocity, let's say v. Okay, common velocity. Okay, common velocity. Okay, this is the common velocity with which they are moving after the collision. Because this is an inelastic collision, so the bodies will stick together and move together after the collision. Okay, but I have told you that there is an in-between phase, right? Where the bodies gets deformed, right? Do you remember, Pranav?
Yeah.
See, there is a deformed state as well, right? In between.
Mm-hmm.
So here in the deformed state, again, line of impact is equal to line of motion here. It is a head-on collision. This is a deformed state. Okay. So in the deformed state, what happens is during deformation, kinetic energy, some kinetic energy is wasted. Okay. For
Okay.
both the blocks combined, some kinetic energy is wasted.
Mm-hmm.
Okay. And when it again reaches this state, then the velocity is such that the initial kinetic energy total is equal to the final kinetic energy total. But here in the deformed state, some kinetic energy is wasted, so kinetic energy doesn't remain conserved throughout the collision. Okay. Okay. Any doubts?
No.
Okay. So I'm not going to derive the conditions here. Okay. Like the conditions which we have derived, applied momentum conservation on these variables and all. We are directly going to jump onto the questions. Okay. Let's do one good question, not a simple one, just based on the formulas and all. This is a mass M. Okay. 9 kg. Here there is a bullet of mass 1 kg. Okay. It is approaching here with an initial velocity of 100 meters per second. Okay. And this is at rest initially. And again, this is attached to a string, which is again attached to a ceiling. Okay. Now, after the collision, what happens? When this collides here, this sticks into it. Okay. Inside of it, the bullet sticks. It means it is what type of collision? Perfectly inelastic. Okay. Now, after the collision, what happens? See, because they will collide together, only x direction velocity is there, right? For this, and here the initial velocity is 0. So after the collision, in what direction will we have to apply the conservation of momentum? Only x direction, right? Because in y direction, no one is going to have any velocities at all after the collision as well, right? And
Yeah.
if you'll ask me why, then let me tell you, like, when, like, assume, what do I say? Real life example, when this type of thing is happening, then after the collision, when the bullet has sticked into this block, then what would happen? It will go something like this, right? It will perform a circular motion. Am I right? Here will be the bullet, and here will be the mass. Total mass would be 10 kg, right?
Hmm.
Something like this will happen in real life. Are you able to imagine it, Pranav?
Yeah.
So here we won't have to apply the like, again, let me write the full question for you. You just have to find out
So do I have to
that,
add attention to this or no?
yeah, there will be tension, but let me complete the question first. So this is height h, which through which it has raised. Both of them, both of the bullet and the mass has been raised. So you have to find just that. Find h. Okay. Options are 5 meters, 50 meters, 0.5 meters, and 0.05 meters. Okay. Now, what we have to do, again, the collision is happening here. So the first and foremost rule when you see a collision being happening is you have to apply momentum conservation. Okay, like, you do, even if you don't know if it is a elastic collision or perfectly inelastic or partially inelastic, you don't have to care. You just have to apply momentum conservation. Why? Because in every type of collision there is external force, there is like no external force. External force is equal to 0. So momentum will always be conserved. About kinetic energy conservation, like initially and finally you can apply everywhere. But yeah, like kinetic energy conservation is one thing, but momentum conservation you can always apply. So first of all, you have to apply that. And if you'll ask me that when it will reach here at the highest point of its journey, then the velocity would be 0, right? It's because the velocity is 0 that it has reached the highest point of its motion, right? In circular motion, this happens only, right?
Yeah.
That the particle reaches its like maximum height when the velocity of the particle is 0. So, but here, there, when it will be at this point, let's say, there will be some horizontal velocity as well as some vertical velocity, right? right?
Yeah.
But the momentum conservation thing that we are going to apply, that will apply before, like at this point, and just after this point. What do I mean just after collision? It means as soon as this block start to move even a little bit. Let's say this angle is theta and theta is almost equal to zero, tending towards zero. It is negligible. So up until this point only, when it has just started to raise upwards, only that point we are going to apply momentum conservation. Why? Because as soon as it will start to ascend, as soon as it will start to attain some height, at that point, an external force, mg and tension, would start to apply. Here, tension and mg are completely balanced. But as soon as it will gain some velocity, it will start to perform circular motion, right? As soon as this combined system of bullet and mass will have some velocity after the collision, it will start to perform a circular motion, right, Pranav?
Yeah.
And when it will start to perform a circular motion with a velocity v, then what will happen? This tension will increase. Why? Because tension minus mg is equal to mv square by r, right?
Yeah.
It means, because this is an equation of circular motion, it means that as soon as this block starts to perform circular motion, it means as soon as this block attains some velocity, the forces will no longer be balanced. Here tension mg are balanced. Why? Because v is zero. There is no v. This v is zero. It means tension minus mg is zero. It means tension is equal to mg. But as soon as this velocity will be non-zero, the tension will be mg plus mv square by r. It means the two forces which were initially balanced are no longer balanced. Okay? Are you understanding completely?
Yeah.
Have you written down all of the things?
Mm-hmm.
Okay, very good. So it means we can apply momentum conservation just until the point, like just after the collision happens. Okay, because just after the collision happens, the objects will attain some velocity. So only up until that point we can apply the momentum conservation. Not even at this point, not even up until this point, not this point, not this point. Okay, only this point. Only when the object is at this point, up until that point only we can apply the momentum conservation. Okay,
Mm-hmm.
so let's apply that momentum conservation in horizontal direction. So can you apply momentum conservation? Can you tell me what should I write?
Horizontally, conservation would be mass initial, so I'll be at 1 times v1, which is 100 meters per second, plus 100 meters per second because it's going on the positive direction. Plus uh the object is at rest, so it'd be basically zero equals
Mm-hmm.
to the mass is just combined, so it'd just be 10 kilograms.
Mm-hmm. And
And
this we don't know.
v, yeah.
So when we are going to solve this down, v will come out to be what? 10 meters per second, am I right?
Yes.
Okay. It means just after the collision, let me draw the diagram over here. Just after the collision, when the mass has become 10 kgs, this is starting to go in this direction with a velocity of 10 meters per second. Right. Now, up until what height it is going to reach, this becomes a question purely of circular motion. Am I right? Hmm? We'll apply what? Work energy theorem.
Mm-hmm.
Are you aware of the work energy theorem?
No, I haven't heard of that.
Like work done by all the forces is equal to change in kinetic energy. This you haven't heard of.
Oh, work is, oh yeah, that one.
You have heard of it, right?
Yes.
Yeah. So the only like uh, what do I say? The only force which is doing some work here, like there would be gravitational force against of which the work is done, and yeah, will there be tension force whose work done we'll have to take? I guess not. Okay, so only the gravitational forces work we'll have to take. So what will be the gravitational force? 100 newtons, right? 10 into G. Pranav,
Yeah.
10 G force would be applied downwards, right?
Yes. Wait, G would consider the acceleration of gravity would be considered as 10 meters per second or 9.8.
Yeah, 10 we'll only consider it to be 10. Okay.
Okay, okay.
Okay. And I guess there will also be a tension force here, right?
Yeah, so
Which we'll have to consider.
that would be a tension
100
upward, that would be
minus T. Yeah. And we'll have to write minus H here. Why minus H? Because 100 into minus H. It means the work done is done against gravity. The gravitational force is downwards and the height is upwards. Right? Upwards it is ascending. Now tension is also upwards, height is also upwards. So it will become plus TH. Okay?
Mhm.
So this is going to be equal to final kinetic energy would be zero because when the velocity becomes zero, it reaches its maximum height, right? So it will be zero minus what? Half mv square, half into 10 into what is v square? It is 10 square. Velocity is also 10, right?
Mhm.
It means uh, t minus 100 into h. This is going to be equal to 500.
Okay.
First equation, right?
Mhm.
And also the tension would constantly be changing, right?
Yeah.
So I think we didn't have to write a T here. Yeah, in these types of questions, the tension we do not even consider. Yeah, that is correct only. Because tension is constantly changing. That is not a
Oh,
constant thing.
should be
Okay.
100 H?
Yeah, only 100 into minus h. Because work done is against gravity, right? So half into 10 into 10 square. It means minus of this thing. Why minus of this thing? Because it is initial. Final is 0, minus initial is this much. Okay. So
Mhm.
minus will get cancelled out. It means h is going to be what? 5 meters. Answer. Okay.
Yeah.
Now take a good look at this whole thing and tell me in case of any doubts. Option A would be correct.